All right. In the previous video, we introduced the idea of representing a straight line in vectorial notation. So we looked at the line y equals 7 minus 2x. So we said we choose any point on the line, for instance 1, 5, and then the position vector of 1, 5, which we denote r naught, is 1, 5. So we use that, and then we add multiples of the direction vector of the straight line. The direction vector for the straight line, since the gradient is -2, then we say the direction vector is 1, -2 for every displacement of 1 in the positive horizontal direction. There is a corresponding displacement of -2. So this could be an example of the vector m. So we said in a point xy, so the position vector of xy on this line, we can write as 1, 5 plus a constant real multiple of the direction vector m. So we said in compact form we can write this as r naught plus tm. M is any real number, it could be plus or minus. R naught is a position vector of any point on the straight line. Then we said in component form, this is saying x is 1 plus t, and the y component going to give us 5 minus 2t. So we said this is called the parametric form of the equation. This first one is called the vector form of the equation of a straight line. Then if you break it down, you get the parametric form. If you eliminate t from the parametric form, then you get what we call the symmetric form. X minus 1 is going to be equal to 5 minus y over 2. So this one is called the symmetric form. So that's as far as we went in the previous video. Now we're going to show another approach of deriving the equation of a straight line, which is going to be particularly useful in when you get to 3D. So this straight line, we know it's got gradient -2. So we know that a line which is perpendicular to the straight line is going to have a gradient 1 over 2. I'm going to call it mn for normal. So normal is for perpendicular. So if we convert this into a vector, we're going to convert it into a vector, and then that vector we're going to call it n for normal. Okay, so that's going to be 1/2 or if we multiply everything by 2 so that we don't have to deal with fractions, it's going to be 2, 1. So vector 2, 1 is going to be perpendicular to this straight line or any other line with gradient -2, but we're just going to do the example or the calculations with this particular line in mind. Okay, so what this means is that so there is our line, that is 1, 5, and a vector n, which is a multiple of this, is going to be perpendicular to our line. Now we can get an equation for this line by doing the following. So we're going to take any point on the line, we're going to call it xy. Now any vector connecting 1, 5 and xy. Okay, so remember this is R naught. Okay, remember this is R naught, or maybe let me, yeah. So this vector here is going to be x minus 1, y minus 5. This vector here, but of course that is simply the position vector of 1, 5, which we just called R naught. It's actually the position vector of R, which is this one, minus the position vector of, is the position vector of xy minus the position vector of 5. But the point we're driving at is that this vector here is perpendicular to this vector. So that means that dot product will be equal to 0. Okay, so if you take this and do the dot product with this vector 2, 1, then this thing must give us 0. So that gives us another way of defining the equation of that straight line. So it's going to be x minus 1 times 2 plus y minus 5 equal to 0. Again, if we make y the subject of the formula here, it's going to be 5 plus 2 minus 2x, which is 7 minus 2x. I'm going to write this a bit compactly. So that thing we can write as position vector of R, which is position vector R, which is position vector of xy, minus position vector of R naught, where R naught is on the straight line, well, and xy is on the straight line. So that's giving us a position vector along the straight line. That's giving us a vector along the straight line that is perpendicular to n. So if we do the dot product of that with n, it's going to give us 0. And so that gives us another way of expressing the equation. Let me just generalize, and then we do maybe 1 or 2 examples. So given a straight line through x naught, y naught, x naught, y naught, and whose normal vector, so that's a vector perpendicular to the straight line. So if the normal vector is AB, which you can write like this or like this, okay, so there is a straight line x naught, y naught. There is the normal vector AB, then the equation of the straight line. So if we choose any point xy here, the position vector of this point is r. Position vector of this point is r naught. Then we're going to have r minus r naught dot n must be equal to 0. R minus r naught is x minus x naught, y minus y naught. This one is a b equal to 0. If we multiply through, this is ax minus ax naught plus by minus by naught is equal to 0. This is ax plus by minus ax naught plus by naught is equals to 0, which is we can write in the form ax plus by plus d is equal to 0, where d is negative of that quantity there. I think you're going to recall this equation in MAT312. We called it the general form of the straight line the general form of the equation of a straight line. Okay, so that's another way we can write the equation of a straight line in terms of vectors. Let's look at one or two examples. Okay, in this example we have a straight line defined by the equation 5x plus 12y minus 67. So want to find the vector form, want to find the parametric form, want to find the symmetric form of this equation of the straight line. Then in part B, want to find the shortest distance from minus 4, 6 to the straight line here. Okay, so for the vector form of the equation, the first thing we need to do is to find a point on the straight line, any point. So the equation is 5x plus 12y minus 67 is equal to 0. So any point on the straight line, if we plug in say x is 1 here, okay, so plug in x is 1, then this thing is 5 plus 12y is equals to 67. So 12y 67 minus 5. That's going to be 67 minus 5 is going to be 62. So what's 62 divided by 12? 62 divided by 12. Oh, it's not going to be a nice number. We want, just for demonstration purposes, want integer values. So let's rather try y is 1 and see how that works out. Y is 1. It's going to be 5x plus 12 minus 67. 12 minus 67 minus 67, 67 not 37, is minus 55. So it's looking much better. So it's going to be 55 this side. So x is going to be 11. So that means one of the points on the straight line is 11, 1, and the position vector for this is 11, 1, like this. Then next we need the direction vector, which we can get from the gradient. So if we make y the subject of the formula here, so 12y is going to be 67 minus 5x. So if we make y the subject, 67 minus 5x over 12 shows us that m is going to be minus 5 over 12. So the direction vector is going to be 1 minus 5 over 12. However, we'd rather deal with whole numbers, so we can multiply this by 12. If we multiply this by 12, then this is 12 minus 5. So we can use that as our direction vector. So we have got the position vector of a point on the line. We've got the direction vector. So the vector form of this straight line is going to be r equals to 11, 1 plus t into 12 minus 5, where t is a real number. So that's the vector form. Then the component, the parametric form, will be 11 plus 12t is x, 1 minus 5t is y. So that's the parametric form. Then the symmetric form, if you make t the subject of the formula here, it's going to give us x minus 11 over 12. This one going to be y, 1 minus y over 5. This one is the symmetric form. Alright, then in part B, want the distance from this line to the point minus 4, 6. Minus 4, 6. So this is the distance we want to find. It's quite a number of ways we can do this. One of them is to find the equation of this line here, which shouldn't be too difficult. So we know the gradient of this line is minus 5 over 12. So the gradient of this one is going to be 12 over 5. So we find the equation of a straight line with gradient 12 over 5 going through minus 4, 6. Then that is going to enable us to find the coordinates of the point of intersection. Then once we got the two coordinates, then we can find the distance. However, a quicker and more elegant approach is to use something that we met in MAT312 called the normal form of a straight line. The normal form is derived from the general form of a straight line. So ax plus by, let's say plus d, because c is so from the normal form, from the general form, we derive the normal form by dividing everything by the square of a squared plus b squared, square root I mean. So square root of a squared plus b squared, then that gives us the normal form. And once you got the normal form, then the shortest distance from any point to the normal form is simply found by plugging in the coordinates of that point. So in our case, the general form of this equation is 5x plus 12y minus 67 equals to 0. So that's the general form. So the normal form is going to be 5x plus 12y minus 67, all divided by the square root of 5 squared plus 12 squared equal to 0. 5 squared plus 12 squared is 169. So the normal form is going to be this thing divided by the square root of 169, which is just 13. So the shortest distance from the straight line to negative 4, 6 we find by simply plugging negative 4, 6 here. Going to be 5 times negative 4, 12 times 6 minus 67, all divided by 13. So we take the absolute value here because we just want the undirected distance. So that's going to be minus 20 plus 36 minus 67, minus 20 plus 36 minus 67. It's going to be 51, negative 51. So that's going to be negative 51 over 13. So this distance is 51 over 13. Just make sure that everything is done correctly here. Twelve times 6 is 12 times 6, 36. 12 times 6 is not 36, so need to do this again. 20 negative plus 12 times 6 minus 67 is minus 15. So just the other way around here. And that's going to be 15 over 13. All right.